So this is so what we are doing is topic 33.3.4. We're talking of the relative ease of hydrolysis. So we have to compare three compounds. One is chlorobenzene, then we have chloroethane, and the third thing is we have an acyl chloride, for example, CH3COCl. So this is ethanoyl chloride. Ethanoyl chloride. So let's compare these three, and what we are trying to understand is how easy it is for us to kick out the Cl and bring the OH. And as I mentioned, this is one of the very repeated exam scenario as well. So if I look at C6H5Cl, which is chlorobenzene, and react with NaOH aqueous hot. Okay, so what you have done this in topic 31, if I'm not wrong. So there you have studied that there is no reaction happening, which means if the chlorine is a part of the benzene ring, so this is chlorine on benzene ring. If the chlorine is attached directly to the benzene ring, it is very difficult for us to remove the chlorine and bring the OH. Okay, then there was a reason given. So I hope you remember the reason. The reason was that the lone pair electrons, this has come in the past papers also many times. So the lone pair electrons of chlorine gets delocalized into the benzene ring. And because of this, what happens? So partial double bond character. So partial double bond character on CCl. So now because single bond is sigma bond, double bond is sigma and pi. Okay, or you could say that the CCl bond is becomes very strong or very less reactive. So since the lone pair of electron becomes delocalized into the ring, so the CCl bond here is very difficult to break. So this is the situation if the chlorine, I'm talking of this CCl bond here. Okay, so this particular CCl bond becomes very strong. So this is what I'm talking about. And the reason is the lone pair electrons of the chlorine is getting delocalized into the benzene ring. Okay, if you have any questions for me, could you type the question or let me know if you have no questions. So we'll go to our next page. So we understand if the chlorine is a part of the benzene ring, it is not going to get replaced by a OH group. Please let me know if I can go to my next page. Everyone is okay? So then what happens if we do this reaction? Now if you look at this one, which is chloroethane, so this represents chlorine on side chain. So this is the best way to learn this. This is chlorine on side chain. If chlorine is on the side chain, you must have studied SN1 and SN2 mechanism in your AS level. Primary halogen alkanes, secondary halogen alkanes does both SN1 and SN2, and tertiary halogen alkane. So this is a primary halogen alkane. It undergoes SN2. So what I can get is I can get the Cl out and I can convert this into alcohol. So this reaction is possible, NaOH. So now we have to understand, okay, so what happened to this CCl bond? Just opening the display formula here. Now you might remember this was also discussed in topic 31. So what we are trying to understand is, so what is so special of this CCl bond here? So this CCl bond is also strong, and the CCl bond in chlorobenzene is also strong. Okay, but this is very strong. This CCl bond is very strong. Why is it very strong? Because the lone pair electrons of Cl has become a part of the ring. So the pi electron system, that the ring here has extended on the CCl bond. So now it's like a sigma and pi bond. So this is very, very strong area. But when it comes to this one, you might remember that the R group here, remember the alkyl group, they do what is called as positive inductive effect. Do you remember positive inductive effect? So the R group or the ethyl group shows positive inductive effect. So that pushing the electrons towards oxygen. Okay. Now, what is the consequence of this on the CCl bond? And this actually makes the CCl bond, because there is greater electron density coming in this area. So the CCl bond is becoming strong, but I'm sure you understand it is becoming strong, but it is not as strong as in chlorobenzene. Making CCl strong, because it is strong, that is why I require NaOH aqueous hot. That is a condition. If I do this reaction at NaOH RTP, there is no reaction. At RTP, there is no reaction. So I need the temperature to be hot. I'm supposed to produce NaCl. Yes, I was checking who's awake in my class. Yes. Thank you. Okay. So we know that. So making the CCl strong, but not as strong as in CCl of chlorobenzene. So we have a, like, we're just trying to compare the CCl of chloroethane. It is strong, but we can break it with NaOH aqueous heat. If we use NaOH aqueous at room temperature, there is going to be no reaction there. Okay, now till now everyone is okay. Everyone is okay. Now we try to understand, so what happened with the acyl chloride? But if I do this reaction, CH3COCl, this is ethanoyl chloride. Now notice the difference. If I work with chlorobenzene, even with NaOH aqueous hot, there is no reaction. When I use NaOH aqueous hot for this one, there is a reaction. But for removing the Cl, I don't even need NaOH aqueous. I can directly work with H2O liquid. So you see the point here. So first point that you notice, that NaOH aqueous not needed. So I can do the hydrolysis very easily, even by using water, and the reaction is going to happen at RTP. I don't even need high temperature here. So now you are very, very clear. Okay, this means the acid chlorides, they can undergo hydrolysis very easily. This is acid chloride. So this is the evidence, and the reaction is happening at RTP. I can just simply use water. So this Cl is going to be kicked out. Okay, so the Cl is going to go. The OH is going to come, and the Cl goes out from here. So I'm sure you can predict what you will get. So you will get CH3CO, and the OH will come. So you get your carboxylic acid, plus you will get H, and the Cl will come from there. Is this equation clear? So I get ethanoic acid. Okay, first of all, tell me, did you understand the equation? Everyone is very clear. Okay. So, but then we have to understand, so why is this reaction happening so comfortably? There must be some reason behind it. Do you have any suggestions why this could be happening so easily? Why the acid chlorides undergo this reaction very easily? What do you think? Any idea? So in case you want to understand this further, so all you have to do is look at the structure here. Oh, sorry. We are talking of CH3COCl, correct? We have to understand why is this CCl bond very weak. This is very weak bond. Why is this a weak bond? It is breaking very easily. So very good. So what you understand is, so okay, so understand this way that both oxygen and chlorine both are highly electronegative, correct? Both are highly electronegative. So what is happening? Oxygen is pulling the electron towards itself. Chlorine is pulling the electron towards itself. So you understand carbon is electron deficient here, correct? So since carbon is bonded to, so how do I write this? So since carbon is bonded to carbon of COCl is bonded to oxygen and Cl, both which are highly electronegative. So carbon is, you understand, carbon is not exactly having too many electrons. Carbon is electron deficient, correct? Carbon is electron deficient, or you can say the CCl bond is very weak. So easier to break, correct? Is very weak or easier to break. So that is the reason why acid chlorides are the easiest to hydrolyze. Okay, so let me give you another example how this question will come. Instead of, yeah, you can say CO is electron withdrawing, which makes the CCl weak. But the issue is the carbon is bonded to both electronegative on both sides. So it's like getting pulled from both the sides there. Okay. CO is electron withdrawing is also a comment which can be used. Okay. So just make a comment that this C double bond O is electron withdrawing. And then you just add up about the oxygen and chlorine also. They are also pulling the electrons in different directions. So the carbon is like pretty electron deficient there. Okay, for example, if the same question comes in this way, okay, so for example, there's a question in which I'm using the benzene ring. Oh, no, sorry. A, B, C. Okay, now you tell me out of A, B, C, if I say I want you to figure out increasing order of ease of hydrolysis, which means most difficult to most easy. Most difficult to most easy to get hydrolyzed. You tell me, let me know when you have the answer. Or you can type in the chat. Which one do you think will be the most difficult to get hydrolyzed? I'm looking at your chart. Please mention. Still no response. Still waiting. Come on, try. Nobody? Which is the most difficult? You're writing? Okay. Okay, fine. I'm waiting. Okay, so what you have to understand is this is COCl. This is Cl and this is Cl. So you understand this way that this is Cl on the ring. This is Cl on side chain. And this is Cl of COCl. Did you get it? So you have to apply what concept you learned here. So this is the Cl of COCl. So the chlorine of the acid chloride is the most easy to get hydrolyzed. So increasing order of acidity, the most difficult will be where if the C should be the most difficult, correct? And then it should be B and then it should be A. Tell me if you understood this. Give me yes or no. CBA, very good. Most difficult, most easy. Do you think explanation will be exactly what we mentioned in the previous page? Do you think explanation will be exactly the same as mentioned in the previous page? No problem at all? Agreed? Yes? Okay. So that's the end of this particular lesson. If you have any questions, this would be a good time. I'm now starting off topic number 34, nitrogen compounds, which happens to be one of the biggest lessons for you. But there is one interesting question I wanted to ask. Hold on, let me just check. This is also another very good question. Okay, what if I give you a question like this? If I give you CH3COCl versus CH3COBr, which will be more easy to get hydrolyzed and why? Which will be more easy to hydrolyze and why? Any idea? This is ethanol chloride. You can write your answers in the chat. And this is ethanol bromide. Who will lose the halogen more easily? Go down to page 2. Yeah, I will. Page 2. Okay, fine. So the Br will be easier compared to Cl. Very good answer. But then any idea why is it like that? The Br will be easy to remove. You see, the thing is, this is, in this case, this is COCl, correct? And in this case, it is CO. If you notice, did you notice the difference in the bond length? Why is it like that? Br is a bigger atom, no? Br is larger than Cl. So the CBr bond length is longer than Cl bond length, and you have studied in your IGCSE and AS level that longer the covalent bond, the weaker it is. So has lesser bond energy, or you can say easier to break. Easier to break. Okay, so the correct answer is the ethanol bromide will be the one who is more easily gets hydrolyzed. So the correct answer is there. Okay, so CH3COBr. So that's the answer. Okay, tell me if you have understood everything. So that's the end of topic 33, and we are now starting topic 34. If you have any questions, I'm waiting. If you have no questions, could you type no, NQ so that we can move on? Okay, so now starting off with topic 34. This is the largest in the organic chemistry. This is nitrogen compounds. So the first thing that we do, 34.1, is formation of primary and secondary amines. Formation of primary and secondary amines. So when I say primary amine, so that is R NH2, or to be more clear, it's going to look like, yeah, you should see the NH2 in any kind of R. So RNH2, or you could say RCH2 NH2, but you'll definitely see the two hydrogens there. When it comes to secondary amine, you're going to see NH. Okay, so you might see a R here and you might see an R here. I'll give you examples. The example of this is, maybe you will see something like this: CH3, CH2, NH, CH3. You're not supposed to name the secondary amine. This is N-methyl ethanamine, but you're only supposed to learn the primary amines naming. Okay, methylamine, ethylamine, and so on. So that's what a secondary amine looks like. You should see the NH in between. Okay, let's have a look. So first of all, how to make a primary amine. Okay, so I'm starting off with the primary amine. So remember, when I say primary amine, I need to see RNH2. I need to see the NH2 there. So one of the things what I can use is by the reaction this you have done in your AS level, I'm sure, by the reaction of halogen alkane and ammonia. This ammonia must be dissolved in ethanol, and you must heat it under pressure, right? If you just say ammonia and ethanol, okay, I'll write and pressure. Okay, if you're ready, let's have a look. CH3, CH2Cl, very simple reaction. Reaction with ammonia. Remember, it has to be dissolved in ethanol and it must be under pressure. So what happens now is that one of the hydrogen is going to go, the Cl is going to go, one of the hydrogen is going to go. So what we get is CH3, CH2, and the NH2 comes in here, and HCl comes in here. Very simple, nice and easy. This is ethylamine. or also called as aminoethane. And as you see clearly, that's the primary amine. So I can take any halogen alkane and just react with ammonia. I can get a primary amine, which means I can even do something like this. So you could go ahead with this equation. So I can give you this equation. I can give you something like this. So as you see here, that's the CH2Br, and I'm going to react with this ammonia. So the Br has to go. So you copy paste everything as it is, and instead of the Br, I have the NH2. In case you're wondering, how do I know that's the primary? Don't forget that what you see here is the CH2 at this end. That's the CH2 there. And I can see clearly the NH2, plus of course I will get the HBr as my secondary product. So that's another example of, it's a nucleophilic substitution reaction that you've done in your AS level. Everything is okay? Let me know if I can just type R for ready, if I can go to my next page. If you have any questions, let me know. So any halogen alkane, I can react with ammonia and I can get my primary amine. Now let's have a look at how do I get my secondary amine. To get secondary amine, which obviously should look like RNH, R. Of course, R can be same, R can be different, it can be anything, but I need to see what is called as the NH. Now, to get that's to get a secondary. No, I did not finish everything from the primary yet. Hold on. Oh, that was the first one. I'm sorry. There's still some more options to get me the primary amine. Okay, just let me do that. So this is by reduction of amides using lithium aluminium hydride. Lithium aluminium hydride. This is a powerful reducing agent. So I have to use lithium aluminium hydride, and I can actually, and of course I have to use my amides. Now remember, amides are the groups containing this link. That's the amide link. You have seen this in proteins and you call it as peptide link. So let's have a look at that equation. So this is CH3CONH2. So the moment you see the CONH2, that's the amide. And then you're supposed to know the names. That's two carbons there. This actually is a primary amide. Once again, the reason why primary is because of the two hydrogens there. It's primary amide. And because there are two carbons there, I'm going to name this as ethane amide. Okay, that's the ethanamide. And what I'm going to do is react this with hydrogens. Now these hydrogens, the moment I write in the bracket, which means they're coming from the reducing agent, which is our lithium aluminium hydride. Now you might come across sometimes, lithium aluminium hydride is kept in dry ether, but Cambridge doesn't want to go there. So you can use lithium aluminium hydride, and you don't have to mention about the dry ether, you can leave it. And what happens now is remember, addition of hydrogen is called reduction. Removal of oxygen is called reduction. Okay, so what's going to happen is I'm going to give hydrogens to this carbon and I'm going to remove the oxygen out. This is removed. Removing oxygen is reduction. Adding hydrogen is reduction again. Okay, so you understand that I need two hydrogens for this one. And then if I get the oxygen out, I need two hydrogens for that one also. So what I get is CH3CH2 NH2. So I got the two hydrogens there. The oxygen that came out, so I need to connect with two hydrogens more. That means I need a total of four hydrogens, two here and two here. And that's why 4 comes in here all the time. Okay, tell me if you understood the reaction. So my primary amide gave me a primary amine. Have you noticed it? A primary amide on reduction gives you a primary amine. Guys, give me yes or no if you're okay with it. Everyone, please. Everyone is okay with it? So the first method I said is take any halogen alkane and just put ammonia into it. Ammonia must be dissolved in ethanol or alcohol, heat under pressure, and you will get your primary amine. Second, use a primary amide and you can do the reduction and you will end up getting a primary amine. So just to practice with using the SKF, because SKF is what usually keeps coming all the time. So let's say I have here CO and that's the NH2. Remember, that's the SKF. And they'll say, okay, how would you do this reaction? The balancing and everything remains exactly the same. As you see here, the moment you see the CONH2, especially when you see the NH2, that's how you come to know it's a primary amide. You want to go ahead and try this reaction? So you will exactly copy the same thing. Now this oxygen is going to go. That's going to become CH2. See, this bit here is becoming CH2. And the NH2 remains as it is. See, this is the CH2 bit here. The CO has gone. Rest everything is the same. Plus, don't forget, you will get here H2O. So once again, what you get is a primary amine. Anyone has any questions? Can you give me on a scale of 0 to 10 where you are? 10 means everything is good. 0 means you don't know what's going on. Or any other number that you want to write. So I have finished with you till now. Two ways how to get a amine, how to get a primary amine. First one done, second one done. Everyone okay? Let's do another one. This is also to get a primary amine. The third way to do it. Reduction of alkane nitrile. Notice carefully, when I say alkane nitrile, I actually don't remove the E. It's alkane nitriles. That's R, C, triple bond N. That's what they look like. Alkane nitrile. Okay? We just write them as RCN. Okay. So reduction. So reduction obviously means adding hydrogen. So I need a reducing agent. So the reducing agent which is used here is I can use lithium aluminium hydride or I can use hydrogen in the presence of nickel catalyst. I can use any of these. Okay, both works absolutely fine. Let's have a look at some equations. For example, CH3 N. Okay, this is just so that you understand what's going on here. That's C triple bond N. I want to add hydrogen. This hydrogen, the moment I put in the bracket, that's basically called nascent hydrogen. The moment I do that, you must understand that's coming from a reducing agent. So my reducing agent, let's say, is lithium aluminium hydride. Now what happens is this carbon, you're going to supply two hydrogens. This nitrogen, you're going to supply two hydrogens. So every time you do this reaction, you just put 4 in front. Are you okay so far? Guys, give me yes or no. You all the time put 4 hydrogens in front. So what comes out is CH3C, and then you put the two hydrogens there, and the nitrogen, and again you put the two hydrogens. See? Two hydrogens, two hydrogens. So what you get is a primary amine again. This is to be called as ethane because there are two carbon, but notice the E is maintained. Ethane nitrile. And what you get here is the aminoethane, but that's the scientific name, aminoethane, but commonly called as ethylamine. Ethylamine is the common name. Okay, everyone is okay with it? But if I do the same reactant with a different, for example, I want to do the reduction, but this time I want to use hydrogen in the presence of nickel. So I want hydrogen in the presence of nickel catalyst. You understand now the balancing of the reaction slightly changes. Because it's H2, I need a total of 4 hydrogens. That's what you learned here. So just put here 2 and you end up getting exactly the same thing. Are you comfortable with it? So if you want to use hydrogen and nickel, put 2 H2. If you want to use lithium aluminium hydride, put 4 in front of the hydrogen H atoms. Everyone okay? Can I go to my next page? Yep. Any questions so far? No problem. I'll wait. Any questions so far? No questions. Okay. Done? Anybody wants me to go back to any previous page? Okay. I hope it's done. So now let's have a look at, so we had like, I think 3 methods how to make a primary amine. First was, if I use a halogen alkane, I can react with ammonia. Ammonia must be dissolved in alcohol, ethanol, and heat under pressure. If I want to work with primary amide, I have to use only lithium aluminium hydride. And the reaction always have 4 hydrogens, 4 written in front of the atomic hydrogen there. If I use a alkane nitrile, I have two choices. I can use lithium aluminium hydride or I can use nickel as catalyst, but the reaction slightly changes. Everyone is fine, yeah? Okay, so now let's have a look at how to make a secondary amine. So all this was for primary amine. Now let's have a look at for secondary. There's only one for making secondary amine. A secondary amine, I need to see R, I need to see NH, and this one. R can be same or different, that's okay. Okay, so let's have a look at an example. To make a secondary amine is by the reaction of a halogen alkane Now, last time we used halogen alkane, we reacted with ammonia. But when we reacted halogen alkane with ammonia, we got the primary amine. Now we are saying we're going to take reaction of halogen alkane and a primary amine. And primary amine must be also dissolved in ethanol. Okay, let's have a look at this reaction. It's very similar to our previous reaction, what we did. Okay, just give me a second. And heated in a sealed tube. I can say heated in a sealed tube, or I can just say under pressure. So obviously you have to keep all the conditions in mind. Let's have a look. So I'm using a halogen alkane. So let's say I want to use CH3CH2Cl. This is chloroethane. And I'm supposed to react this with the primary amine. So let's say I'm using CH3, for example, CH3NH2. This is a primary amine. This is aminomethane. Common name, methylamine. So remember, this reaction, the primary amine must be dissolved in ethanol. Okay, not the whole thing, but the primary amine, just like we dissolved ammonia in ethanol. See, this ammonia must be dissolved in ethanol. Similarly, we are saying the primary amine also must be dissolved in ethanol because primary amines are coming from ammonia. Okay, so how does that work now? The reaction is exactly the same. You kick one Cl out and you kick one H out. This is also called as a condensation reaction. This is condensation reaction. In condensation reactions, these things happen. H2O, HCl, smaller molecules are eliminated this way. Now, very, very important for you to understand that the way this molecule has to be now represented, you have to flip the molecule the other way around. Okay, which means it's going to be written now. See, I'm going to start writing from there. So that's CH3, CH2. Now the Cl is gone. Okay, so this has to be written the other way around. So you have to swing it this way. So what that means is one H is gone. So now I have the NH and the CH3 coming from the other molecule. And plus I have the HCl. Notice how I wrote it. The NH and then I have to swing it the other way around. This is important. Okay, so that you see is a secondary amine. According to the curriculum, you're not supposed to name the secondary amine. I'm just writing it for the sake of entrance. This is called N-methyl, and that's two carbons there. So that's ethane amine. But remember, the syllabus says no need for that. So that is my secondary amine. Okay, do you have any questions for me so far? Any questions so far? Everyone is okay? Guys, yes or no? No questions? Okay. So let's try to work a simple one. Okay, could you name these compounds, please? What is the name of the first compound? What is the name of the first compound? At the second position, there is a methyl group. So this, and then you have to, at the first position, there is a bromo. So you have to tell me the bromo position first. So 1 bromo, 2 methyl propane. Correct? Very good. What about the next one? So 1 amino, because A comes first, 1 amino, 2 comma 3 dimethyl, 2 comma 3 dimethyl butane. Okay, okay. Either say under pressure or say heated in a sealed tube. Either you can say heated in a sealed tube or under high pressure. Both are okay. Okay, so now what happens? The Br goes and one H will go. And don't forget, you have to swing this molecule like this. So I will get like this. That's coming from there. And then I need to connect the NH. And then I have 1, 2, 3. So that's 1. The methyl group is on the second position. That's the methyl. That's 3. There's a methyl at the third position. That's 1. See, this is 1. This is 2. This is 3. And then I have carbon number 4. This one here. Plus HCl. Okay, give me yes or no if everyone is okay. That's your secondary amine. All good? So I'm done with preparation of primary and secondary amine. So we studied 3 ways to make primary amine, and there is only one way that we have to know how to make a secondary amine. I'm just saying, not mentioned in the syllabus, but if I want to make a tertiary amine, you know what I have to do? I have to take halogen alkane and take a secondary amine. So what you have to understand is ammonia gives primary amine, primary amine gives secondary amine will give tertiary amine. So basically one hydrogen will keep knocking out. Okay, so that's the end of this part. We are now starting the next subheading. Any questions so far? So we finished 34.1, the first one, how to make primary and secondary. Now, after that, the next what we have to do is we have to figure out the condensation reaction between ammonia or amine with acyl chlorides to give amide. So we are now looking at basically formation of the amide. This is 34, topic 34.1.2. Okay, so just to summarize where we are, so topic 34.1, point number 2, which says we need to figure out the, hold on, just we just confirm, formation of amide. Okay, like how do I get an amide? Once again, just remember the amide looks like this. This is what an amide looks like. So how do I get it? So there are two things what we have to look at. Hold on, I'm just looking at where I'm. Okay, A part. By the reaction of ammonia with acyl chloride. Oh, sorry, just a second. Acyl chlorides, they look like this. Okay, let's have a look at some examples. Is my product not okay? Oh, product is HBr. Thank you. Okay, so let's have a look here. So simple reactions, CH3 COCl reacting with ammonia. Would you like to go ahead, try to complete these equations? Let me know when you think you finished. Very simple reaction. All these are still condensation reactions. You will do exactly the same thing. Get rid of the Cl and get rid of one of the H. Let me know when you finish. And don't forget, you have to swing it this way. Let me know when you're done. Type DN for done if you finish. So what you should have got was CH3CO and you should have got NH2. Is that what you got? Plus you will get HCl. Okay, did you notice that this is a primary amide? Correct? This is ethane amide. This is an example of a primary amide. How do I know it's a primary amide? Because you see the NH2 there. Okay. And what about this one? This is called benzoyl chloride. Benzoyl chloride. So I should be getting something like this again. So that's the CO and the Cl is gone and I should get the NH2 plus the HCl. Correct? This is called benzamide. Yes, you have to know these names as well. Okay, everyone is okay so far. Simple reaction. Any acyl chloride, if you react with ammonia, you will get amide, and that too you will get primary amide. Is that clear with everyone? Okay, so what we are getting is reaction with ammonia. Make a note, to get primary amide. Okay, so are we ready for the next page? Let's see what happens if I take an acid chloride and react this with a primary amine. Now let's see what happens. Okay, this is the A part. B part. By reaction of acyl chlorides with primary amines like RNH2. So what we understood in the previous one, if I react with ammonia, I will get a primary amide. So you probably might guess now, if I react with a primary amine, what kind of an amide will I get? Obviously, I will not get a primary amide. So I think you probably might have guessed that you will end up getting what is called as a secondary amide. Okay, secondary amide formed. So how does a secondary amide look like? So this is a C double bond O. See, this is called a primary amide. So when I say a secondary amide, it looks like this. So there is a R here and there is a R here. Did you see the difference? Okay, this is what a secondary amide looks like. Just to be sure that you understand. So if I have an amide which looks like this, you see the nitrogen has two hydrogens. This nitrogen has one hydrogen. Did you see the difference? Can you give me yes or no? This amide is a primary amide. Are we clear with the difference, please? Everyone on a scale of 0 to 10, are we clear with the difference? A primary amide, CON, the nitrogen must have two hydrogens. But a secondary amide, the CON, the nitrogen will only have one hydrogen. I need everyone to confirm that you are perfectly fine. Okay, so let's have a look. So I have here CH3 COCl. So I have my ethane oil chloride. And I'm reacting this with a primary amine. Okay, so let's say I want CH3NH2. So this is my primary amine. How do I know it's primary? Because I see the NH2 there. So this is methylamine. Okay, so why don't you go ahead with this equation? And once you finish, you can try this one. Okay, go ahead and tell me if you finished. HCl will be formed, correct? Because one Cl and one H will go. This is okay. Can you figure out the names of these compounds? That will be very good if you can. That's carbon number 1, carbon 2, carbon 3, 4, 5, and 6. Any idea what's the name of this compound? That's carbon number 1, carbon 2, carbon 3, carbon 4, carbon 5. On third position, there is the ethyl group. So this is 3 ethyl and there's a 6 carbon. So that's hexane oil chloride. And this is 1 amino 3-methyl pentane. Everyone is okay with the name? 1-amino 3-methyl pentane. Let me know when you're done. Don't forget, you need to swing this the other way around. Please type DN for done if you finish. Name of the reaction, condensation reaction. Have you done? So you should have got CH3CO. Then I will get NH because one H is gone and the CH3. Is that what you got? Oh, sorry. We're making amide. Sorry. Yeah. Okay. We got it right. CO, NH, CH3. Is that what you got, guys? And as you notice, this CONH, this is a secondary amide. And according to the syllabus regulations, there is no need for you to know how to name the secondary amides. So what you understand is the primary amine gives you a secondary amide. You try this one. So I'm just going to copy the first thing as it is. So, oops. So that's 1, 2, okay. Okay, that's done. Is that what we got? 2, 3, 4, 6. Okay, good. Everything okay? And then on the other side, I have the NH. You write it like that. And then I have like going up to 5. So that's 1, 2, 3, 4, 5. And on the third positions, 1, 2, 3. Third position, there is a methyl group. Is that what you got? Please confirm your structures. You are also able to write this in the structure formula, correct? That's a CH3, CH2, CH2, CH in the bracket C2H5, and then CH2, CONH, and then CH2, CH2, CH bracket CH3, and then CH2 and CH3. Could you please confirm if my structure formula is correct? Guys, please confirm. Is that correct? Okay then. So we know now how to make a primary amide. We know how to make a secondary amide. So what we understand is if I react with ammonia, I will get a primary amide. But if I react with a primary amine, I will get a secondary amide. And the syllabus says you react with amine. So they didn't tell which one. So we have to now look at the third option. Third option is what if I do the reaction with a secondary amine? What will happen then? So let's have a look at the third one. This is, I think you can guess now what will you get. So this is the third one by the reaction of, I hope everyone is okay, by the reaction between, we are going straight off, no break, reaction between acyl chlorides and secondary amines. Any guesses which kind of amide will you get? Till now what you understood, if I work with ammonia, I will get primary amide. If I work with primary amines, I will get a secondary amide. But if I work with a secondary amine, what amide do you think I will get? I will obviously get a tertiary amide. right? This is to form tertiary amide. So how does a tertiary amide look like? A tertiary amide must have a C double bond O N. Notice carefully, the nitrogen there doesn't have any hydrogens. It will have a R and a R. There is no hydrogens on it. So what you understand till now, if there are two hydrogens, that's primary. If there's one hydrogen, that is secondary. And if there's no hydrogens, that's your tertiary. Okay, let's have a look at some examples. So if I give you C6H5COCl, CH2, NH, CH3. Okay, go ahead, do this equation. Past papers particularly will test you using SKF. Let me know when you've done or if you need any help. So you have to connect this bit with this one. Okay, so you got to connect that bit with this one. Have you done? How do we write it? Okay, hold on. So you should have got C6H5CON, and then you see there is a CH3 and there is a CH3CH2. So what would normally we recommend? Put the smaller one in the bracket and put the bigger one as the parent. Okay, so this is an easy way to write it. Have you understood? Put the smaller r in the bracket and the bigger r goes in as a parent chain. Got it? So what you see is the CON. That's your tertiary amide. Let me know if you all are clear. Is that okay with it? Okay. And what about this one? So if you want to make the SKF of that, so that's the benzene ring. And then that's the, you could, okay, that's the C, hold on. So what you could do is you can just put like this. That's the C double bond O, and that's your N. And then you put, okay, now what happens? N has a bond here. That's the CH3, and that's the two carbons. Got it? That's the CH2, CH3 there. That's the CH3 there. And that's the CON that you see here. That's the benzene ring. Okay? And how do we do this one then? So you just copy out as it is. So that's the C double bond O, all done. And then what I do is I remove the H from there. So I need to put an N, and I know N has got like how many? See, this is already connected here, right? So I have an N. Okay, so N is supposed to have like 3 bonds. So what do I do? Is there something missing in the structure? 1, 2, 3. Okay, that H is gone. Okay, then I have, hold on. There you go. Plus, I have the HCl. Something is not right. Is there something missing in the structure? Guys, there's something missing in the structure. Hold on. It's supposed to be C double bond O and then there is a N. Okay, so this is fine. N is supposed to have 3 bonds. So that's okay, it's all good. The CON and that. Okay. And here I just want to check the bonding on around the N. Just give me a second. So I have here N. The H is gone. But where's the third link? Do you see what I'm saying? I hope my secondary amine is correct. Yeah, so the H goes, N comes in, N has a CH3. What is missing? I'm slightly getting confused. I'm sorry. Anyone can open the mic and tell me? This has to go. Am I missing a point? I'm not missing a point? Okay. Okay, so that's the N comes in here, correct? So the Cl is gone, N comes in here. Okay. And I have a CH2, that bit is there. Oh, we did not look at that bit. Okay. So there is this bit, CH2, CH2, CH3. So that means there has to be a bit like this, CH2, CH is CH2, CH2, CH3. And then I have this bit. Now is it correct? Check. Or completely missed this one. My bad. Okay. Is this okay now? It's okay. We completely missed this particular bit. Yep. Okay. So that is again the CON, my tertiary amide. Is everything okay now? Okay. Can we convert this into SKF as well? Let's try this. Have you tried the SKF of this one? So that's the C double bond O. That's the N. That's the, so I need to have a CH3. So just stick one line there. And then that's a CH2, CH2, CH3. Okay, now it's okay. All good? Please let me know. That's the CH3. That's the CH2, CH3. Okay, all good. Okay, any questions so far? So we're done with how to make amide. So we know how to make a, where are we? How to make a primary amide. A primary amide, we just react acyl chlorides with ammonia and we get a primary amide. No problems there. And then if we use a primary amine, then we end up getting a secondary amide. And if we use a secondary amine, then we end up getting a primary amide. Everyone is okay? Okay, good. So that's the end of how do I make an amide. So the next thing, which is the third topic, this is topic number 34.1.3. This is to explain basicity of amines. Basicity of amines in solutions. Like, why are amines base? Okay, so let's understand how this goes. First point, keep in mind that the amines are obtained from ammonia. Correct? We get all the amines from ammonia. So what does that mean is, if I remove one hydrogen out and replace that with one R group, I get RNH2, which is a primary amine. First, let's understand from where they come from. And if I take the same NH3 and if I'm going to remove two hydrogens and I'm going to put two R groups, I get RNHR. I get my secondary amine. Do you see what's happening? I hope you're seeing what's happening. So if I take ammonia and if I knock out all the three hydrogens and replace them with 3R, which could be same, could be different, I end up getting a nitrogen connected with three same or different R's. In a very simple way, I get R3N. So this is my tertiary amine. Once again, you notice that a primary amine has two hydrogens. A secondary amine has one hydrogen on the nitrogen. A tertiary amine has got no hydrogen on the nitrogen atom. First of all, okay, Sonia, can you just tell me which one are you talking about? On which page number? Page number 10 or page number 11? The primary amine. Okay, a primary amine. So basically, what that means is from an ammonia, if I take one hydrogen and replace with one R group, so it becomes RNH2, correct? So if I see RNH2, I'm going to call that as a primary amine, which is obtained by removing one hydrogen from ammonia and replacing with one R group. If I replace two hydrogens with two R groups, I get secondary amine. If I replace three hydrogens, all the three, and replace with three R groups, I get tertiary amine. Okay, that's what it just talks about. How many hydrogens am I replacing? Okay, now why did I say all this? We know that ammonia is a base, correct? Why is ammonia is a base? I'm sure you have studied this from the IGCSE days. Why is ammonia considered as a base? Ammonia is considered as a base because it's a proton acceptor. And why is able to accept the proton? Due to lone pair electrons on the nitrogen. Correct? You have done this reaction so many times that ammonia can accept a proton because nitrogen has lone pair of electron. It can accept that proton easily and changes into NH4 plus. In your AS level, you have studied VSEPR theory. You know this is 107 pyramidal, this is 109.5 tetrahedral. The bond angle increases because lone pair changes to dative bond, so the repulsion becomes less. All that you have studied before, correct? So ammonia is acting as a base. So why did I say that? Because if ammonia is acting as a base, does that make sense that amines also should be acting as a base just like ammonia? Because amines are coming from ammonia. Does that make sense? Give me on a scale of 0 to 10. Amines comes from ammonia. Ammonia is a base. So amines also must act as a base because they also have nitrogen. Nitrogen has lone pair of electrons. It can accept the proton with a dative bond. Does that make sense? Please give me a scale of 0 to 10. 10 means makes sense, you understand. 0 means you don't know what I'm talking. How clear you are on this idea? Okay, so let's have a look. So amines are bases since they can accept protons, and this is due to lone pair electrons on nitrogen atom in amines. So it doesn't matter it's primary amine, secondary amine, tertiary amine, all of them are bases. They all have nitrogen. Nitrogen has lone pair of electrons. So if you look at very simple equations like CH3, CH2, NH2. So you know this is ethylamine and you are giving it a proton. Okay, so the parallel, what I want you to understand is if ammonia gains a proton, it changes into NH4 plus. What is the name given to it? You say this is ammonium cation, correct? And I'm sure you remember conjugate acid base pair. So this is the base. So do you remember this is the conjugate acid? Give me yes or no. Do you remember? Because ammonium is a proton donor now. Guys, I need to tell me if you remember this. Ammonia, after accepting a proton, has become ammonium. Ammonium is the conjugate acid of ammonia. Is everyone clear? Okay, good. Now, apply the same logic here. Apply the same logic. Nitrogen has lone pair of electrons. So it is going to take that proton. So it will change into CH3, CH2, NH3 plus. Now this is similar lines. That's why I wrote ammonium cation here. This is now called ethyl ammonium cation. Now you will say, why am I calling it ammonium? It is not NH4 plus. It is not NH4 plus. It is ethyl ammonium. One hydrogen has been replaced by the R group. It's ethyl ammonium cation. Ethylamine is a base. Ammonia is a base. Ethylamine is a base. Ethyl ammonium cation is the conjugate acid of. Did you see the connection between this, what I'm teaching? Ammonium cation is the conjugate acid of ammonia. So ethyl ammonium cation is also the conjugate acid of ethylamine. Everyone's okay? Comfortable? Correct? So I can give you anything. I can give you something with benzene. If I give you phenylamine, this is called phenylamine. Yes, you can call this aminobenzene and you react this with a proton. So what do you think you will get? The NH2 changes into NH3 plus and this is called phenyl ammonium cation. So why are amines bases? Very simple, because amines, they are all derivatives of ammonia. They have nitrogen. Nitrogen has lone pair, and because of that they can accept the proton very comfortably. So that's the end of this particular discussion. If you have any questions for me, let me just go through the pages. If you have any questions so far, this is what we did. We started the session with hydrolysis. So we understand the Cl on the ring cannot go because of the CCl is very, very strong. The Cl on the side chain can go with NaOH hot, but the Cl of the acyl chloride goes very easily. The CCl is very weak because of those reasons. We did some practice questions on ease of hydrolysis. How do we make amines, primary amines coming in from ammonia and halogen alkane? If I use reduction of an amide, then also I can get primary amines. Reduction of alkane nitriles, that also gives me primary amines. But if I do reaction of a primary amine with halogen alkane, I get secondary amine. So that's one way to get a secondary amine. That's the only way. Then how do we get amide? If I react ammonia with acyl chloride, I get my primary amide. So I need ammonia to get primary amide. But if I use primary amine, I will get secondary amide. And if I use secondary amine, I will get tertiary amide. So this is the situation there. Okay. Then Basicity of amines, we understood amines are all coming from ammonia. So as ammonia acts as a base, amines also act as a base. Okay, I'm waiting for any questions that you have. If you have no questions, could you please type NQ? NQ means no questions. Anybody wants me to go back to any previous page? So we are now doing 34.2, which is phenylamine and azo compounds. So that's the heading. 34.1 is completely finished. In 34.2, the first thing is, how do we prepare phenylamine? This is one of the very, very important questions, which is also part of topic 36, organic synthesis. Okay, so they want you to know, how do I make phenylamine? So it's a part of a long chain of questions. So I'm just going to mention 34.2 point number 1. So this is a preparation of phenylamine. We have done this. Phenylamine, this is how the syllabus also addresses it. It's also called as aminobenzene, which is C6H5NH2. So how do I put NH2 on the benzene ring? So if you remember the previous, it's always good to keep revising that big long chain, because so if I start with benzene, do you know how to change benzene into nitrobenzene? Remember, how do I change benzene into nitrobenzene? What do I need? Mention that in the Zoom chat. I need concentrate HNO3 plus concentrate H2SO4. Then temperature 25 degrees Celsius to 60 degrees Celsius. Okay, what else? What else do I? Everything is, that's it. The name of the reaction is electrophilic substitution. That's the temperature, no? 25 degree to 60 degree. Concentrate HNO3. And then this reaction is called electrophilic substitution. And once I have nitrobenzene, then what should I do? If I want to directly change nitrobenzene, I have to then react this with, if I want to change this into, let's say this, phenyl ammonium cation. So what should I do in the second stage? Tin plus hot concentrate HCl. This is reduction, because removing oxygen is called reduction and adding hydrogen is called reduction. This is phenyl ammonium cation, correct? This is phenyl ammonium cation. Now what do I do? I have to remove the H out as an H plus. I have to do deprotonation. How do I do deprotonation? I react this with NaOH aqueous. I get rid of the H plus there. So what I will get is the phenylamine. Everyone okay? So that's how I get my phenylamine. So I just practiced from benzene. Benzene changed to nitrobenzene. From nitrobenzene, you will change to phenyl ammonium cation. And once the NO2 changes to NH3 plus, you do deprotonation, and then you will change to NH2. Okay, is everyone comfortable? We have done this before, I think, if I'm not wrong. If everything is okay, please let me know if you have any questions. Otherwise, we are now going to start the reactions of phenylamine. Guys, let me know if everything is okay now. I will just do a couple of reactions before we end the session, since we went directly. Everyone okay? So we are now doing topic number 34.2.2, which is the reactions of phenylamine. Very easy reactions. I'm going to finish that to finish off our session today. We don't have too many reactions to do. So there are two main reactions to study. One of them is the reaction with bromine solution, with bromine aqueous. Now this is interesting because if you remember the reaction of benzene with bromine, you might remember that was liquid bromine and you had to use FeBr3 and heat. Do you remember? Catalyst was required, no? FeBr3. Bromine liquid was required. That was reaction with benzene, and even with methyl benzene, that was a condition required. But here, if you notice, it says I can do the reaction with bromine aqueous. Later on, we'll be talking why the difference. So now what happens? So this is phenylamine. You are reacting with bromine aqueous. It is very important you do that because in the exams they'll ask about the state symbols, particularly here. Because there is a difference. If you react with benzene and methyl benzene, you have to take bromine liquid. But if you take phenylamine, you have to work with bromine aqueous. So there is a difference. What you will understand is this reaction goes similar to phenol. All the three positions, because you might remember NH2 is a ring activator. How many of you remember that? Do you remember NH2 is a ring activator? Remember that? NH2 is a ring activator. What do you mean by ring activator? It pushes the electrons into the benzene ring, increases electron density at position 2, 4 and 6. Remember this? Increases electron density at position 2, 4 and 6. It makes the polarization of electrophile more easy. These are very, very key sentences Cambridge always looks for. So what that means is I'm going to get Br at position 2 and at position 4 and at position 6. Plus I will get 3 HBr. Similar reaction with phenol. So you put here 3. This is 2, 4, 6. Tribromo phenylamine. And this comes off as a white precipitate. Any questions so far? Is everyone okay? Please let me know. Okay. Hold on. The next one, what we have to do, okay, how much? Okay, we have a bit of time. I'm just looking at the curriculum. Just give me a moment. Our next reaction should be reaction of phenylamine, okay, to form diazonium salt. Okay, let's have a look at one more reaction before I end the class. Is that okay? That's the last one for today. This reaction is with HNO2 or NaNO2. I'm just mentioning what the syllabus says. With HNO2 or NaNO2 and dilute acid at 0 to 10 degrees Celsius to produce diazonium salt, diazonium salt. And let's have a look at how do I make the diazonium salt and what can we do with it. Last reaction for this particular session. But there are a few things that you need to keep in mind. So HNO2, this is called nitrous acid. Okay. And NaNO2, this is sodium nitrite. Sodium nitrite. Okay. Now what happens is that I need HNO2, which is nitrous acid, and the problem is it's very unstable. Okay, this is actually pretty unstable. This is very unstable. So it's very difficult for us to keep this in a chemistry lab without it's not getting broken down. So what we do is we react HCl and NaNO2. Okay, so these two react together to form NaCl plus HNO2. So we are actually going to produce HNO2 within the reaction, and that's how we actually do it. So when they say dilute acid, they were referring to HCl. So HCl and NaNO2, they react together and they produce the HNO2. Okay, so that's one of the main reactant that we are. So we are not adding HNO2 from outside, we are producing it in the reaction itself. So my recommendation is when they ask you reagent, say NaNO2 and HCl. Okay, so let me give you a simple equation to work with. The reaction says I need to react phenylamine, so that's the phenylamine NH2, and I'm reacting this with HNO2 plus HCl. Now, if you look at the marking schemes, they might say, okay, allow NaNO2 plus HCl. Okay, so they will say allow NaNO2 plus HCl. They will say allow that. But as I said, NaNO2 is only a source to produce the HNO2. That's the main reactant. So let's use that only. Temperature must be 0 to 10 degrees Celsius. So that's a temperature condition, 0 degrees Celsius to 10. It must be very, very cold temperatures. Older papers might even say ice cold conditions. Okay. So what happens in this? I will get what is called as this compound, which is N2Cl. This is benzene diazonium chloride. This is the diazonium salt they are talking about. Plus I will get the water. Now, very important, on further warming, which means if I allow the temperature to slightly increase, so this is the product which I got, the benzene diazonium chloride. I will explain this once again in the next session. So this is N2Cl, this is H2O. If I allow the temperature to slightly increase, because temperature must be maintained 0 to 10. So what happens now? The benzene diazonium chloride undergoes hydrolysis and it starts to break up its groups in this way. It changes into phenol. So that's basically how we end up getting a phenol. And the N2 comes out as nitrogen there. And the H and the Cl, they connect together to form the HCl. So that's how you get OH on the ring. Okay. So that's a very, very good reaction there for you. And benzene diazonium chloride, I will teach you in the next class, is also used to make azo compounds. I'll tell you how they are formed. Azo compounds are used as dyes in textile industry. Okay. So remember, phenylammonium chloride, phenylamine reacts with nitrous acid. Remember, this is nitrous acid, and at 0 to 10 to form benzene diazonium chloride. And this benzene diazonium chloride, if you allowed it to continue reaction with water, slightly elevated temperatures, will eventually give you phenol on the ring. That's the only way to get the OH on the ring according to in our curriculum. So Okay, so that's the end of our discussion for today. In the next session, I'll continue with more reactions and we'll go more deeper into topic 34. If you have any questions, this would be a good time. I hope the session was okay. Let me know if you have any questions. I'm waiting.